Hey guys, guess where I am and guess where you're not. If you look behind me, pretty empty these days. So I wanted to give you a quick video so that you can kind of know what we were supposed to be doing today, Thursday, and tomorrow, Friday. So that way you have a sense of how to get your homework going, get the paper done, get WebAssign done, and you can ask me still through Remind with any questions that you might have, okay? So, yep, hope you enjoy your weekend, and we better have school on Tuesday. Hi guys, hope you've had a good snow week. I want to make a little video for you so that you kind of have an idea of what we're supposed to cover this week, and that way you can get all the stuff done that you're supposed to get done. I've been sending out numerous reminds, so hopefully you've subscribed to Remind and you're in our chat so you know what's going on. Okay, a quick recap of what we missed about total distance traveled versus net distance traveled, which was a few lessons ago. So I want to do a quick recap on that, and then my goal is to actually take you through these notes here, day 98 and day 99, and take you through those pretty quickly so you have a good sense of how to do the homework in WebAssign and also the stuff you have on paper. As we're not having school this week, all the paper stuff, we'll talk about on Tuesday, should there be school on Tuesday. All right, so first, if I'm given some velocity function here, you can see the graph here on the right in red. And this function is only defined from t equals 0 to t equals 3. So only during the first 3 seconds is the particle actually, do we care about it? Question 1 is find the net distance traveled. So the net distance is just also known as the displacement of the particle. So we're not particularly concerned about the fact that it's like turning around. We don't need to consider anything of that as a factor. And you can see that I have up here 2 different ways to express v of t. So here in blue, I've got v of t equals 3t squared minus 7t plus 2. And then I factored it below as the quantity 3t minus 1 and the quantity t minus 2. So if you want to find net distance traveled, the antiderivative of velocity is going to give me position. So I need to find out what is the displacement, that's an integral, to get from velocity to position. From which time, so now I'm looking at the yellow highlighted stuff over here. What is the time that I'm concerned about? I'm concerned about the time from 0 to 3. So those are my bounds in my integral. And what is the function that I'm integrating? V of t dt. Okay? Now I'm going to look at what I've highlighted in green here, and I'm just going to take the antiderivative of v of t. So what is the antiderivative of t squared? That's t cubed. What is the antiderivative of negative 7t? Negative 7 halves t squared. What's the antiderivative of 2? 2t. Now there's technically a plus c here, but because we have a definite integral, meaning I have bounds on my integral, I don't have to worry about the plus c's. The c's cancel out. I do need to indicate, though, that I'm evaluating this from 0 to 3. Okay? And if we do all that, remember when we evaluate a definite integral, that means we evaluate the whole thing at 3 first. 3 cubed minus 7 halves times 3 squared plus 2 times 3. That's the first bit. I'm just plugging in 3 everywhere there's a t. And then we're subtracting all of this evaluated at 0, which is 0. So all of that is just minus 0, which really we don't need to write. So we need to figure out what 3 cubed is. And when you do all the math on this, you're going to get an answer. 2, 9, 63 halves plus 6. And when you figure out what that number is, that should be your solution. Okay? So the next question is, how are you going to find the total distance traveled? By the way, in case you're wondering, my fluid math crashed in the middle of this video, so that was super exciting. It's like you've missed absolutely nothing from what happens in class every day, which is the technology that I have crashing. So that's exciting. So here's the graph of v of t. And if we want to find the total distance traveled, we're concerned about the integral from 0 to 3, because remember, our time is from 0 to 3 here. Time t equals 0 to t equals 3. That's what we're concerned about. So we want an integral of that. But we're going to consider the fact that for some of this time, namely on the interval from like a third on the graph is about right here, to 2, the particle's velocity is negative, which remember means it's moving left. So from t equals 0 to t equals 1/3, the particle is moving right. And from 2 to 3, it's moving right again. So here it's moving right. Here it's moving right for this little bit. But in between here, the particle is moving left. So we've got to consider all of that. And we need to consider the total distance traveled. So we're going to take the chunk that is right, take the other chunk that he's moving right, and then take the chunk that he's moving left and add it all together. So in effect, what we're doing is we're taking the absolute value of this function, which means if I take the part that's left right here, this little bit, and I reflect it across the x-axis, there we go. That's the absolute value of v of t. Okay? So the absolute value of v of t is this blue graph right here. There it is. And what that will allow me to do is find the area under the curve, and then the new area here, this part, will no longer cancel out with the positive area. So if you go back to where we were, and you find the area under the curve, like we did in part 1, where we said, hey, let's clear ink notations. We said, hey, let's find the net distance traveled. The net distance traveled is just like, hey, figure out this area, and this area, and this area to 3, right? And then just let those areas cancel each other out. For example, this area here is negative, but these areas are positive. So the net distance traveled is less. Total distance traveled, though, doesn't let this negative area cancel out with any of the positive stuff that we have over here because it reflects it across. So all of it's positive, which means we get the total distance traveled regardless of direction. So it's the absolute value of v of t dt. And very often this is a calculator active question, these particle motion problems, so you'll be able to just enter this right in the calculator and get the answer. And it'll be in decimal form, and that'll be fine. WebAssign, though, doesn't really like it. So for that reason, you have to split this up into some different integrals. So for the first part here where it's positive, that little bit, you need to express that as an integral from 0 to where? Where does it change signs? Well, that's where 3t minus 1 here is equal to 0, which happens at 1/3. So from 0 to 1/3 of v of t dt. Okay, and I need to figure out what that integral is by hand, just like we did with net distance traveled. Then I'm going to add the integral from 1/3 to where does the negative stop? It stops at 2 of v of t dt. Now when I calculate the integral from 1/3 to 2 of v of t dt, the one I just wrote down, that's going to be a negative value. So I want to make sure that I consider the fact that it's going to become positive. I want it to become a positive number. So if I put a negative in the front of it, a negative times a negative will result in a positive number. And then I'm going to add the last integral, which is from 2 to 3 of v of t dt. So hopefully that brings a little bit of clarity to you on how these WebAssign things work when it comes to net distance versus total distance traveled. And WebAssign's picky, so it's not going to take, the decimal answer that you're going to get here and give you credit. You need to actually find it by hand. And this is the process here of how to go about finding what the total distance traveled is by hand. Okay, off we go to the notes for the last few days. So the first one here, definite integral as a accumulation of change. So we already know that the derivative of an amount is the rate at which that amount is changing. For example, if water being drained from a swimming pool, that's what's occurring, and R of t represents the amount of water measured in cubic feet that is in a swimming pool at any given time, then R prime of t would represent the rate at which the amount of water is changing. So if we take the derivative of R of t, then we get R prime of t. What would the units be of R prime of t? Well, remember that R prime is like the slope of the tangent line. So it's the change in y over the change in x. Okay, and y here is cubic feet. And the change in x is time, so cubic feet per hour. And remember that an integral is an antiderivative. It's just taking a derivative going backwards. So if you start out with an amount in a derivative, the derivative of an amount leads to a rate. So if you start with a rate and you take an integral of something that is a rate, you will get an amount. So another way to think about the integral is as an amount of change. So in the context of that example situation above, what does the value of r prime of t integrated from a to b represent? It represents the amount of water drained. So this is the amount of water drained from when to when? From my upper bound to my lower bound. Okay? Since it was a rate to start with, the integral of that rate returns an amount. And now we have a table that represents the velocity of a particle in terms of values of t, and t is measured here in minutes. So we have to approximate the value of an integral from 0 to 30 of v of t dt. And they ask us to use a midpoint Riemann sum. Okay, the first thing we're going to do here is explain what we're trying to do, which is find an integral from 0 to 30 v of t dt. Now we're not going to be able to come up with an exact amount because we have a table. That's why the key word here is approximate. Okay? And just like a secant line is an approximation for a derivative, a Riemann sum is an approximation for an integral. It's an approximation for the area under the curve. Okay, now we're going to find out we need to use a midpoint Riemann sum. We're going to use correct units of measure. So if I'm going to divide this, I'm going to go from 0 to 10, my midpoint Riemann sum there, 10 to 20, and 20 to 30. Okay? The width of my rectangle, is it consistent? Yeah, it's always 10. Okay, what is the midpoint value? The midpoint value is the height of the rectangle, so those are the y values, and those y values are in the middle, midpoint, midpoint, midpoint. Remember, you get a point for setting this up, so make sure you set it up correctly. 1.6 is the first one, 3.1 is the other, and 1.6 again. Okay, when you do all the math there, you get 63 feet. Using correct units of measure, explain what the value represents. So what are my units of measure? Feet, that's the amount of change. Remember, we started out with a rate, and the integral of a rate is an amount. So we're going to get rid of the feet, or rid of the minutes, the units, and get feet. Okay, what does this represent? It represents the amount of change. So the amount of change from when to when. From t equals 0 to t equals 30 seconds. Okay. So now for part B, what is the value of an integral of a of t dt from 5 to 25? Whoa. Well, we don't have any acceleration in this table at all. But we do know something about the antiderivative of acceleration. The antiderivative of acceleration is velocity. So the antiderivative of the acceleration function is going to give me velocity. And I do have some values for velocity in our table, right? So what I'm going to do here is go ahead and write out how I would go about solving this. The bounds are from 5 to 25, so don't forget that. That's important. So the integral from 5 to 25, a of t dt, is going to equal the velocity function. But that velocity function is a definite integral, meaning there are numbers here on each side of my integrand. Limits, we call them, limits of integration. So v of t gets evaluated from 5 to 25. So another way for me to write that is to say, hey, take the top value, evaluated the top value, v of 25, and then subtract the bottom value evaluated in the velocity function. V of 25 minus v of 5. I can look at the table and actually find out what those values are. V of 25 is 1.6. What is v of 5? Another 1.6. Subtract those. What do I get? 0. What does that represent? It represents the amount of change in the velocity of the particle from t equals 5 to t equals 25. Okay, on the back page. The temperature of water in a tub is modeled by a strictly increasing twice differentiable function. When a function is strictly increasing, that means it's always greater than 0. And it's twice differentiable, that means you could take the derivative 2 times, where w of t is measured in degrees. Okay, we have to estimate the value of w prime of 12. The key word? Estimate. What are we estimating? A derivative. How do we estimate a derivative? Secant line. Do you see a 12 in the table? No, because you picked the values around 12. So again, we're going to write the steps that lead to the correct answer so we can get the points for the process. Okay, I want to find w of 9 minus w of 15, change in y over change in x, over 9 minus 15. And when I do that, I end up with 1.017. Remember, round to the thousandths place. What are my units? It's a derivative, it's a rate. Degrees Fahrenheit is the y value, divided by the x value, which is minutes. What does this mean? What is the meaning of this? It's a one-sentence thing that's going to give you all the points here. And you have to state that the temperature of the water is increasing, because this value is positive, increasing at a rate of 1.017 degrees per minute at t equals 12 minutes. Okay, the second part here, how are you going to find the integral from 0 to 20 of w prime of t? Well, what is the antiderivative of a derivative? In other words, if I'm trying to take an integral, that means I'm finding an antiderivative. W prime of t is a rate, right? So if I'm trying to find an antiderivative of a rate, I just get the original thing. So another way to think about it is 0 to 20 of w prime of t dt is going to equal w of t. But it's not just w of t plus c, because there's a 0 and a 20 in my bounds. So I'm evaluating from 0 to 20. What does that mean? That means I'm going to take w of 20 and subtract w of 0. How do I do that? I use the table. What number do I get? 16. What are my units? The amount of change, degrees. What's my explanation? The water temperature has changed by 16 degrees Fahrenheit over a span of how many minutes? 20. Okay. This next question is a calculator active question. And what you end up doing here is taking, for the function w that models the water temperature, this is the first derivative right here. What is the temperature of the water at t equals 25? Okay, notice that w prime of t only applies from 20 to 25. Okay, that's important. Also, do we know what the temperature of the water is at 20? We do. We're told what that is at the table here, 71 degrees at t equals 20 minutes. So just like the previous problem, we're going to set up an integral from 20 to 25 of w prime of t dt. We're going to let the calculator, math 9 is FNINT. That's how I'm going to figure out what this is. And I know that this answer is some number that my calculator will tell me, but I know the integral of w prime of t dt is w of t. But it's w of t not plus c, but evaluated from 20 to 25. Okay, which means on the right side of the equation, what I'm going to get here is w of 25 minus w of 20. Remember that w of 20 we came up with in the table. It was 71 degrees, so I'm going to go ahead and plug that in there. Okay, I'm looking for the temperature of the water at t equals 25. So I'm looking for this number right here. I don't know what that is. I have to isolate that. And how do I figure out what's on the left side of the equation? I'm going to plug all this into Math 9 on my calculator. Obviously, this is my y1 in my calculator, and I'm going to find out what that number is. And it is 2.043. So if I want to isolate W of 25, that means I have to add 71. So the temperature of the water then, W of 25, is going to be 71 plus 2.043, which is 73.043 degrees Fahrenheit. Okay, that concludes those notes. Let's look at the other notes and see if there's anything particularly tricky on here that we need to discuss. So these are the notes that would be going on tomorrow if we had school. And it's always, these story problems are always very, very exciting. So as you'll learn later in the year, there's like a potato problem. That one's world famous. And the memes are just amazing. So here a pan of biscuits is removed from an oven, at which point in time t equals 0 minutes. The temperature of the biscuits is 100 degrees. So usually this amount becomes important somewhere in the problem. The rate at which the temperature of the biscuit is changing is modeled by this function. It's nice that they called it b prime of t to remind us it's a rate. Okay? If we need to find the value of b prime of 3, okay, we need to figure out what the derivative is at t equals 3. Now a lot of students will look at this and say, oh, I know I'm going to use n derive. But remember that the function is already b prime of t. So all you really have to do is plug this thing into your calculator, call this your y1, go to the table, find out what happens when x is 3, and you get a value, b prime of 3, is negative 8.236. And remember, I'm rounding to the thousandths place. And what are my units? Degrees, because it's temperature of the oven. And what are my time units? Minutes. Degrees per minute. And it's negative 8.236. What is the meaning of this in the context of the problem? Well, I know that at t equals 3 minutes, what is occurring? The temperature of the biscuits is is it going up or going down? Well, since my derivative is a negative number, that tells me that the temperature of the biscuits is decreasing. At a rate of negative 8.236 degrees per minute. Okay, now I have to sketch the graph of b prime of t on the axis below. Explain in the context of the problem why the graph makes sense. So what you're doing now is setting an appropriate viewing window on your calculator. And the graph looks something like this. Okay, what are we looking at the graph of? This is b prime of t. Okay? So, why does the graph make sense? Because the temperature of the biscuits is gradually going to acclimate to the temperature of the room. In other words, the rate itself, and we're looking at the rate is increasing all these tangent lines are positive at a decreasing rate. Okay, at t equals 10, what is the temperature of the biscuits? So remember at the very beginning, I looked at the question stem and highlighted that 100 degrees. I have a feeling it's going to come into play right here. So if I want to find the temperature of the biscuits, what I have is not the temperature function. I have the derivative. Okay, and that's the rate at which the temperature is changing. So if I want to know what the temperature is, I'm going to need the integral to figure out what the temperature is. So that means I'm going to need an integral, and this is going to be an integral of b prime of t, which is going to give me the temperature. I need bounds on my integral because I want to know at time t equals 10. Well, what time am I going to start at? I'm going to find out the amount of change between t equals 0 minutes and t equals 10 minutes. because I know that that's b of 10 minus b of 0. Now you may say, well, Mr. Vandermeer, how did you know that you were going from 0 to 10? And I would say, that's a great question. Do you know how I know? Because I read the question stem, and the question stem gave me only one value. They gave me only one temperature in the entire problem, and that's at t equals 0 minutes, the temperature is 100 degrees. Had they said, hey, at t equals 5, the temperature is 100, I would have said gone from 5 to 10. But the only one I have is 0, 100 degrees. In fact, usually what I encourage my students to do is at the top of their paper, go ahead and write that down, that coordinate. You know, at t equals 0, you're going to get b of t is 100. If you write that at the top of your paper on the test, on the AP exam, you'll remember it in part C or D when they ask you for it. And you'll know what to use. Okay, how am I going to find the integral from 0 to 10 of b prime of t? I'm going to use my calculator. I go to math 9 in my calculator, F N I N T, and I end up with negative 65.817. What's b of 10? We don't know. We're solving for that. What's b of 0? That's 100. Isolate b of 10, add 100 degrees to negative 65, and you get 34.183. Now remember that you can use common sense for all this stuff. And what I mean by that is if your answer, like on this potato problem you're going to be doing here pretty soon, if your answer is negative 332 degrees, clearly something went wrong. So go back and, you know, look through things and see if you can make sense out of chaos. Okay, this cylindrical can problem, I will let you do on your own. I have sent you the key through Remind. It's very similar to the problem on the front. So I hope you enjoy your weekend, and hopefully I'll see you on Tuesday.